Next, the same practice we can do here, logarithmic p series. In the first case, we have to show that the integration 2 to infinity dx upon x into log x raised to p, where p is positive constant, converges if and only if p greater than 1. It was the consideration of integral part. In case B, we have to see that what implications does the fact in part A have for the convergence of the series sigma n is equal to 2 to infinity 1 upon n into log n raised to p. Let us see the tabletop. First of all, we have to consider this integration. Integration is from 2 to infinity dx upon x into log x raised to p. Since it is improper integral, we have to write as limit b tends to infinity 2 to b dx upon x into log x raised to p. To solve this directly also we can write, but let us go by simplified way. Let us take log x is equal to y. So, we can write here 1 by x dx is equal to dy. We can see that at the limit x is equal to 2, y is equal to log 2, and at x is equal to b, y is equal to log b. So, here limit b tends to infinity, integration is from log 2 to log b 1 upon y raised to p dy. So, this is equal to limit b tends to infinity y raised to minus p plus 1 upon minus p plus 1 from log 2 to log b. Here we have mentioned that p is different from 1 because denominator is minus p plus 1. So, limit b tends to infinity 1 upon p minus 1 into 1 upon log 2 raised to p minus 1 minus 1 upon log b raised to p minus 1. So, when we apply the limit, in the case of p greater than 1, it is 1 upon p minus 1 into 1 upon log 2 raised to p minus 1, and in the case of p less than 1, we can see that it is infinity. Therefore, this integration 2 to infinity dx upon x log x raised to p is convergent for p greater than 1 and divergent for p less than 1. Now, let us consider separately for p is equal to 1. When p is equal to 1, the integration looks like 2 to infinity dx upon x log x. This is limit b tends to infinity integration 2 to b dx upon x log x. So, what happened? The next term is limit b tends to infinity log 2 to log b dy upon y. So, when we substitute the limit, it is finally limit b tends to infinity log of log b minus log of log 2, and the limit implies that it is nothing but infinity. So, the finally the integration 2 to infinity dx upon x log x raised to p is convergent for p greater than 1 and divergent for 0 less than p less or equal to 1. Slide please. So, in the first case, we have proved that the integral is converges if and only if p greater than 1. Definitely it will be implied to the in case of series also. When we consider series for n is equal to 2 to infinity 1 upon n into log n raised to p, it will be convergent for p greater than 1 and divergent for p less or equal to 1. Next slide. Now, an interesting theorem which is known as comparison test. Let sigma an be a series with no negative terms. The first case is sigma an converges if there is a convergent series sigma cn with an less or equal to cn for all n greater than n for some integer n. So, in the first case we have seen that there is comparison between two series. If we know that terms with bigger terms, series with bigger terms is convergent, then the series with lesser term is definitely convergent. In B case, sigma an diverges if there is a divergent series of non-negative terms sigma dn with an less or equal to dn for all n greater than n for some integer n. In B case, we can see that if the series with lesser term is divergent, that means its summation of series is infinitive, then definitely a series with bigger term is divergent. Here by simple comparison we can see the proof of this theorem. Let us see on the tabletop, please. Here sigma an is convergent series, sigma cn is convergent series that we have accepted. Now we have to consider about sigma an. So we can say that see that a1 plus a2 plus an, this n is capital, plus a capital N plus 1 plus and so on. This first series can be considered as less or equal to, in this way, a1 is less or equal to a1, a2 is less or equal to a2, an is less or equal to an plus 1 less or equal to cn plus 1, it is given there, and so on. So from here onwards we are considering series cn. So the next term is a1 plus a2 plus a3 plus an plus sigma ck, where k is running from n plus 1 to infinity. Now we know that this series is convergent series. So it has some finite value, plus adding these finite values we have some finite number m, because sigma cn is convergent. So we have seen that positive term series a1 plus a2 an up to infinity is bounded by this number m, right. So here when we consider sequence of partial sums, that is also bounded by this number m. Therefore by last theorem we can say that this series is convergent series, right. We can see here the sequence of partial sums s1 less or equal to s2 less or equal to s3 less or equal to sn less or equal to m for all n, right. And therefore Sn is convergent, and so sigma an is convergent, right. Let us see B part. Here we have to show that sigma an is divergent series when sigma dn is divergent, which has lesser terms than an. The same thing here, the series a1 a2 an plus 1 and so on greater or equal to a1 plus a2 and so on. From here we can see that an plus 1 is greater or equal to dn plus 1, an plus 2 greater or equal to dn plus 2 and so on. So the term is a1 plus up to an plus series sigma k n plus 1 to infinity of dk. Now this series is given that it is divergent series, its summation is infinite because it is positive term series. So the whole is infinite. So we can see that the summation of sigma an is greater than infinite, therefore sigma an is also divergent. Slide please. So we have seen this comparison test. Next, a very good application of comparison test is for the factorial series. Here factorial series sigma 1 upon n factorial is described as 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus 1 upon 3 factorial, and we have to show this series is convergent by using this comparison test. One hint is also given on the screen that 1 plus sigma 1 upon 2 raised to n, if we make little comparison between these two series, then we can prove that this series is convergent. Let us see comparison on tabletop. Here the first term 1 is less or equal to consider as 1. Then the next term is 1 upon 1 factorial less or equal to again 1. The next term 1 upon 2 factorial less or equal to, we can write 1 by 2. The next term 1 upon 3 factorial less or equal to we can write 1 upon 2 square. Similarly, 1 upon 4 factorial less or equal to 1 upon 2 cube. So in general, we can write 1 upon n factorial less or equal to 1 upon 2 raised to n minus 1 for all n. So the comparison can be considered in this way: the first term of factorial series, second term, third term, and so on, 1 upon n factorial up to infinity less or equal to the first term with first term, then 1, second term is again 1, plus 1 by 2 plus 1 upon 2 square plus 1 upon 2 cube. Let us write down 1 upon 2 square, 1 upon 2 cube, and similarly 1 upon 2 raised to n minus 1, and so on. Here we can see that this is actually a geometric series with ratio 1 by 2. If I consider from here, the first term is 1, ratio is 1 by 2. So this is geometric series. Since ratio is less than 1 by 2, this is convergent series. So by direct comparison test, we can say that the right hand side is a geometric series with this, and therefore by direct comparison test we can say that left hand side series is also convergent. Slide please. Next. Now the next is limit comparison test. Here, given that a n and b n are positives greater than 0 for all n greater or equal to some fixed integer n. The first case is if limit n tends to infinity, a n by b n is equal to c, which is some fixed constant number and positive number, then sigma a n and sigma b n both converge or both diverge. Keep in mind, let us repeat it again. Limit n tends to infinity, a n by b n is equal to some non-zero fixed constant which is positive, then sigma a n and b n both converge or both diverge. If limit n tends to infinity, a n by b n is equal to 0 and sigma b n converges, then sigma a n converges. Third case, if limit n tends to infinity, a n by b n is equal to infinity and sigma b n diverges, then sigma a n diverges. It has very interesting proof. Let us see the tabletop. Here it is given that limit n tends to infinity, a n by b n is equal to c, where c is greater than 0. The limit it exists, so we can start with for any epsilon. So let us start with epsilon is equal to c by 2. Here we have chosen epsilon is equal to c by 2 greater than 0. For this epsilon, there exists an integer n greater than 0 such that for all n greater than n implies mod a n by b n minus c less than c by 2. So this inequality can be written in this way, that minus c by 2 less than a n by b n minus c less than c by 2. So let us add c with all the terms. So it is c by 2 less than a n by b n less than 3 by 2 c. Now multiply all the terms by b n, because b n is greater than 0. Definitely we can do that. So this implies c by 2 into b n less than a n less than 3c by 2 b n. This is possible because b n is greater than 0. Now this inequality suggests that sigma a n and b n both converge or both diverge. Because of this inequality we can say that. Okay, slide please. Now the next one is limit is 0 for a n b n and sigma b n is converges, then we have to show that sigma a n converges. Let us see the tabletop please. Here given that limit n tends to infinity, an by bn is equal to 0 and sigma bn is convergent. This is given information, right? And we have to show that sigma an is also convergent. Let us start with for any given epsilon greater than 0, we can have some n greater than 0 such that for all n greater than n implies mod an by bn less than epsilon. Since an and bn both are positive, we can simply write an by bn less than epsilon, and therefore we can write an less than epsilon bn. This is possible because an is positive and bn is positive. Now, due to this inequality and by direct comparison test, we know that since sigma bn is convergent, we can write sigma an is convergent. Okay. Similarly, let us see slide please. Third case. In the third case, it is given that limit n tends to infinity, an by bn is equal to infinity, and we have to prove that sigma bn, it is given sigma bn is divergent is given, then we have to prove that sigma an divergent. Let us see on the tabletop please. Here given that limit n tends to infinity, an by bn is equal to infinity with the sigma bn divergent series. For this we start in this way. For given positive integer m greater than 0, there exists some n greater than 0 such that for all n greater than n implies an by bn less than m. This gives us an is greater than m bn. By this inequality and by comparison test, since sigma bn is divergent, we can say that sigma an is divergent, right? Let us see slide please. Next. So here some of the cases are given. Definitely you can try it for your reference. The first series is 2n plus 1 upon n square plus 2n plus 1. Second series is 1 upon 2 raised to n minus 1. And third is 1 upon n log n upon n square plus 5. In all the three